So far we have discussed different aspects of spectrophotometry, but never ventured into specifics. Now, in the last slide I had shown you number of parameters that are prescribed for the determination of drinking water quality. So, it is obvious to us that the water should be as pure as possible, but in the given circumstances several water bodies in India are as of now stand polluted. Therefore, it is important for us to determine the several metal ions, especially non-metals also, including surfactants, anions and cations. Sometimes we are expected to do the analysis of alkalinity and then hardness, all these things, including the phenolics, oils, etc. But we have spent lot of time and efforts to make complete water analysis using spectrophotometry. That is the beauty of this course. In this course, what I am going to teach you is selected spectrophotometric procedures which will give you a procedure for the determination of these metals or non-metals or surfactants as the case may be. But we also will tell you how to prepare the reagents. We will also tell you a little bit about the nature of the complex, and then we will give you a cookbook value that if all the reagents what you use are good and accurate, they do not contaminated, then what should be the standard value you should get. So, that is known as cookbook value. A cookbook value tells you tells you that when you do an experiment, if you get the cookbook value, what we have written in the book, if you get it, that means all your reagents are pure, your laboratory is pure, your chemicals are pure, and the method is reliable. And all these data we have collected, done in our laboratory and several times repeated. They are all standardized, averaged and within the acceptable limits. So, if you are able to determine the buy or collect the chemical reagents and water, etc., then you do a standard sample, and then with the standard sample, if you get the correct value as reported in this course, if you get it, the analysis is within your control. We also try to give you certain information about the interference of the other metals, anions, etc. I will emphasize as and when we come across these things. And another point I wanted to tell you is that if you refer to number of books, you will come across same procedure. Okay. And the problem is that sometimes the procedure tells you that you must add your reagents, dilute it to 10 ml, dilute it to 100 ml, dilute it to 50 ml, like that, before you make your measurement and go for calibration curve and do the unknown as per our procedure so far we have discussed. Now, earlier, about 20 years before, to some extent even now, spectrophotometry was not considered as a reliable method for the chemical analysis. There are two main reasons for this. One is the spectrophotometry as practiced since last 100 years has undergone a sea change. So, earlier people used to have very small instruments, colorimetry, colorimeters, Lombard colorimeter, and then eel colorimeter, etc., where you could do in the laboratory, but none of them were standardized, because none of the methods were standardized with respect to the instrumentation. Nowadays, very good instruments with gratings, prisms, etc., and very accurate electronics has improved quite a lot. Stability of the noise stability also has improved quite a lot. So, the reproducibility has improved. Therefore, given all these things, we feel that spectrophotometric result should be accepted as a standard. This is our effort to make the spectrophotometry as a standard. So, what we have adopted in this procedure, in this course, is all the solutions are to be diluted to 10 ml final solution. I do not want you to dilute to 25 ml, 50 ml, 100 ml. There are several books write the different procedures, but the fact remains that for all spectrophotometric procedures you require only 5 ml of the solution, only 5 ml, that is 5, you can imagine 1 square centimeter cell can hold hardly 3 ml, 2.5 through 3 ml is more than enough for measurement. So, there is no point in preparing a solution for Beer-Lambert's law checking for 50 ml dilution, it does not serve any purpose. So, what we have decided is we will use only microliters for the preparation of the samples. Still it will give you a reliable value, and the final volume of dilution should be 10 ml. So, with this introduction, I would also like you to remember that most of the information has been collected from the standard methods of analysis, but all of them have been modified to make your reagents within the experimental errors, and also to whenever you make a preparation of the method, it should be reliable. So, with that in mind, I would like to continue our discussion for different parameters in the next 4 or 5 classes. Okay. So, coming back to the determination of boron. So, what is boron? Boron is a micronutrient. Okay. Almost all plants, what we mean by micronutrients is all the plants and animals, human beings, including human beings, need boron. It is a part of our physiological system. So, the boron should be determined in all drinking water. Now, I want to tell you a fundamental truth also, that is, any substance in excess is a toxic element, any substance, including water, including salt, what we eat daily for our daily survival. So, any substance that is part of our environment must be monitored, whether it is micronutrient, whether it is an essential element or non-essential element, does not matter, because if the concentration exceeds the particular limit, anything can become toxic or carcinogenic. For example, if God has made this oxygen pure, then all of us would have been burnt or oxidized long back. Therefore, God has diluted oxygen with 80% nitrogen, otherwise oxygen is a very corrosive element. Similarly, salt, with salt 5 milligram of 5 gram of salt or something like that per day, we are all very comfortable, but the same thing if the concentration doubles in our daily uptake, we are all in trouble. Same thing is true with respect to other salts. For example, sodium chloride is a common salt what we eat daily. We can feel the taste, but suppose it is lead chloride or lead acetate, then it has no taste, but the concentration if it increases and goes in our body, it will cause the damage to the same to the extent that it is capable of. So, that is not desirable. So, what is important is, irrespective of whether a substance is carcinogenic or non-carcinogenic, if it is part of our environment and part of our physiology, we should determine that element in our drinking water and food and other things also, but here we are concentrating on the effluent, drinking water, etc. So, if somebody is letting out these chemicals into the environment, it is essential that we monitor it, right. So, coming back to boron, boron is an essential element. So, we work for the determination of boron. Now, boron gives a bluish red color with carmine, that is the reagent we are proposing. In that carmine has to be dissolved in sulfuric acid. So, the next sentence here says after 45 to 60 minutes of absorbance is measured. That means, the complexation of carmine with boron in sulfuric acid medium is maximum around 45 to 60 minutes, and the substance is absorbing at 585 nanometers, that is within the visible range. And because boron is part of the glass, borosilicate glass, we should not determine boron in glass vessels, we should use plastic vessels. Very simple logical explanation and requirement of the procedure. Now, what are the requirements? Here you can see that the reagent, first we give this is the style of the cookbook also, that is first we give the reagents, how to prepare the reagent. That means, you have to prepare standard boron solution, and standard borons, as I have told you yesterday, that 1 to 5 ppm or very low ppm solutions are not stable. Therefore, we prepare what is known as a stock solution. A stock solution is about 100 ppm, which is stable for long time. For this, what you have to do? You have to calculate how much of boric acid corresponds to 100 ppm of boron. So, boric acid is H3BO3 and boron is only a simple element, and if you calculate the molecular weight and simple chemistry, you will remember, you will know that we have to dissolve 0.0572 gram of boric acid in 50 ml of hot deionized water. You have to cool it, make it up to 100 ml in a polythene volumetric flask. So, Carmine reagent, how do you determine Carmine reagent? How do you make it? Of course, you cannot synthesize all organic compounds in the laboratory, that is understood. Therefore, what you should do is you should buy it. These reagents are available across the shelf with chemical suppliers. So, if you take 46 milligrams, that is 0.046 gram of carmine in 100 ml of concentrated sulfuric acid, that too again you should use a polyethylene volumetric flask, and it will dissolve and give you a reagent. Now, what you should do? Because you are doing the experiment in in the laboratory, you have to prepare 20, 40, 60, 80 and 100 microliter of the standard boron solution into 6 different polyethylene beakers to make the Beer-Lambert's calibration. So, I have to tell you that 1 microgram per milliliter is 1 ppm. So, if I ask you to prepare 100 ppm, that means 1 ml, 1 milliliter will correspond to 100 micrograms of boron. You can go show the slide, please. Okay. So, 100 ppm will have 1 ml. That means, if I want you to take 20 microliters, here I want you to take 20, 40, 60, 80, 100. So, if I take 1 ml, I will get 100 microliter. If I take 0.8 milliliter, that is 80 microliters, I get 80 micrograms. Like that, we have to prepare 20, 40, 60, 100 microliter of the standard boron solution in 6 different polythene beakers, add the required amount of water to make the volume almost up to 1 ml. Then you add 50 microliter of concentrated HCl to keep the sample in acid medium. Then add 5 microliter of the concentrated H2SO4 and mix and allow the solutions to cool. Then you have to add the Carmine reagent, mix and transfer to dry 10 ml polyethylene. After 45 to 60 minutes, you will measure the absorbance at 585 5 nanometers. Now, once you make the measurement, once you make all the solutions and make the measurement, etc., you have to prepare a calibration curve. So, from 20, 40, 60, 80, 100 microliters, what you have developed the color, you take it to spectrophotometer, make your measurement, and then you have to prepare a calibration curve by plotting absorbance versus concentration and determine the concentration of the sample by referring the absorbance of the sample to calibration curve. So, how much sample you should take is the question, because quite often you do not know the what is the contamination level. So, this is a sort of judgment you have to do as an analyst. Normally, we recommend, using our experience, that you must take 1 ml of the sample that will come within the experimental Beer-Lambert's law range. So, the cookbook value is 6 ppm. Boron gives you an absorbance of about 0.31 plus or minus 0.01. That means, you go back, you prepare all your calibration curve, and then 60 microgram, that is in 10 ml, would be 6 ppm. Okay. 60 by 10 is 6 ppm. This 60 microgram will give you absorbance of 0.31 plus or minus 0.01. And to do this, you need to prepare, you need to be prepare yourself for a high quality laboratory work using milliliters or microliter pipettes. And if you continue doing the experiment, if you get 6 ppm 0.31 absorbance, all is well. That is the speciality of the cookbook value. If you do not get it, what you should be doing is go back to your reagent, check your reagent, check your pH, check your chemicals, check your operator handwriting, check your pipettes, whether they are broken or something like that. If you do not get 0.31 plus or minus 0.01, something is wrong. So, but if you get it, go ahead with the remaining chemical analysis. That is the beauty. So, this is the characteristic absorption spectra for carminic acid, boron and boron carminic acid complex. So, the number 1 is the boron carminic acid, and number 2 is the sample. So, 3 is another sample. So, like that different 585 nanometer is somewhere here. So, this peak we are normally monitoring or somewhere here. The molecular, you can see that molecular absorption peaks are somewhat complex, but you need not worry about it, because the at the recommended range it should be possible for us to determine within reasonable limit the specifications of the water sample with respect to boron. Now, this is the calibration curve. You need not check only 0.6 ppm, you can check any of your absorbance values between 0, 2 ppm, 4 ppm, 6 ppm, 10 ppm, etc. You can see that it is a reasonable absorbance curve, fairly linear, and the linearity does not change up to 8 ppm. 9 to 100 we have seen some absorbance variation from Beer-Lambert's law, where the sample absorbance will be lower than this. Okay. So, this is I am giving you the cookbook value also, as well as Beer-Lambert's law. Now, we do have certain information about the pollution, about the interferences of other metals, that we will take a look as and when we require. And for the time being, what I would like you to do is, if you are able to understand all the nuances, and if you have a spectrophotometer at your disposal at 585 nanometers, you go ahead, do this, and you will be able to determine boron in from 1 to 8 ppm, and that is the range in which you will find most of the water bodies in India, approximately showing you the concentrations in their matrix. So, that brings me to the next one, determination of chloride. So, in the chloride, what I would like you to do is, I have to inform you a little bit about the importance of chloride in the method and the environment. The chloride is a ubiquitous element, it is not part of our nature. The chloride comes to us from the soil, and most of the soil is having chloride as a content, and since the earth is having lot of chloride on the surface of the soil, and it has been raining since millions of years, what is happening is most of the chlorides, soluble chlorides, have dissolved and gone to the sea. That is why sea water is very salty. All the sodium salts and potassium salts are highly soluble in water, and because of the rain, all of them have taken out the chloride and sodium and potassium chlorides from the surface of the soil into the sea. That is why we see lot of chloride. By the same analogy, we do not get lot of bromides and iodides, fluoride also to that matter, because fluoride is not part of the natural cycle in the of the element. Same thing is true with bromide. You do not find bromine as a natural element anywhere in the world. Same thing is true with iodine, you will not find, but sodium bromide, sodium iodide, etc., they are all in the sea water. So, chloride is important for us, because whenever we take out water from the surface water or from the well water or from rainwater or somewhere, chloride is always associated with the water, and chloride imparts certain amount of dry taste to the water. Chloride of course is not desirable in industrial situations also, because chloride normally will form scales. Chloride, sulfates, all these things will form scales in the pipelines, etc. Not good for health. Normal river water contains about 130 to 150 ppm of chloride. If you look at the slide what I had shown you earlier, the WHO standard prescribes about 100 to 500 milligram per liter, that is ppm of chloride, and the chloride should be within that limit. So, the chemistry of this refers to the reaction of mercury thiocyanate to liberate the thiocyanate ion. So, it is a very simple reaction. So, whenever there is chloride in the water, we add mercury thiocyanate to liberate the thiocyanate ion, and the liberated thiocyanate ion forms a red complex with added ferric iron. That means, we add a little bit of ferric iron also, and it is very well known reaction that ferric thiocyanate is a very dark red color measured at 460 nanometer, that is proportional to the quantity of the chloride in the sample of water, because thiocyanate liberates the chloride reacts liberating thiocyanate to the same amount of equimolar in the ratio. So, what we need is stock chloride solution, that is about 1 gram of sodium chloride at 105 degree centigrade, and we have to dissolve, to get this solution we have to dissolve 1.01648 gram of anhydrous sodium chloride in deionized water and make up to 100 ml. So, from this we prepare the working solution of 10 ppm, that is dilute 10 times. How do we do that? We take 10 ml of the stock chloride solution to 100 ml with deionized water, I get 10 ppm. Now, I need to prepare mercury thiocyanate. All these procedures are already available in the book, but here our aim is to make them work at very low concentrations and less chemicals in the environment. So, we dissolve 0.417 gram of mercuric thiocyanate ion in isopropyl alcohol and make up to 100 ml with the same isopropyl alcohol. So, we also need ferric salt. So, the best salt to get ferric in reproducible form is ferric ammonium sulphate, and you should take about 11.555 gram, that is 0.25 molar you have to prepare, and 11.555 gram of ferric ammonium sulphate must be added to 6 ml of concentrated nitric acid. So, that can be dissolved. You see, generally what happens is, if the concentration, if the ferric ammonium sulphate does not contain so much of acid, it will precipitate. That is why we say use concentrated nitric acid for ferric ammonium sulphate. And you can dissolve it in 50 ml water and make it up to 100 ml. So, the procedure again as usual, I have to take 1, 2, 3, 4, 5 ml of 10 ppm standard chloride solution in different 10 ml flasks, add 1 ml of ferric ammonium sulphate, 1 ml of ferric thiocyanate to each, and then that will liberate the equal quantity, stoichiometric quantity of chloride, dilute to 10 ml with deionized water, and after 10 minutes measure the absorbance of each solution in a spectrophotometer at a wavelength of 460 nanometer against the blank. Of course, I do not have to overemphasize that we have to carry out the blank, because every water you come across nowadays will have certain amount of iron that will turn red the moment it comes in contact with the thiocyanate ion. So, taking it further, we have to prepare a calibration curve and then use usual way. We have to have a recommended sample volume is about 0.2 ml and cookbook value is 1 ppm of chloride, that is a standard in 1 centimeter cell should give you an absorbance of about 0.19 plus or minus 0.01 ppm. And this is the spectrum of the ferric thiocyanate that is produced. You can see that the substance is having a lambda max somewhere around 630 or something like that, and earlier what we have said is 460 nanometer. This is somewhat orangish in color, 460. So, we are looking at this range because the liberated ion will have lower color. So, absorbance should decrease from the standard. So, maximum decrease is the point where the measurement is being made. So, 460 is the ideal one. In quite good spectrophotometers you may get 464, but in ordinary spectrophotometers you may get 460, 465, 455 like that. So, we are saying 460 you go because the concentration versus absorbance curve is almost flat in this range, not much difference. Okay. So, this is the calibration curve. You can see that the linearity is given by y is equal to 0.003 x plus or minus 0.003. This refers to intersection very less. So, it must pass through the origin, and the concentration, the linearity, the slope is 0.997, almost 1. Therefore, it is approximately at 45 degree angle to the sample. So, we will stop here and look at other parameters in the next classes. I would like you to remember as far as possible the reagents, reaction conditions at least for water analysis, and I urge you to read this colorimetric methods of analysis by E. B. Sandel as well as volumetric this Vogel. So, thank you very much. We will continue our discussion in the next class for other pollutants. Thank you.